All right, we're going to talk about something a little more complicated this time, and it's Chapter 18, Section 2, Reversible Reactions and Equilibrium. So as we go through this, try not to get too freaked out about it if you're having trouble kind of understanding exactly what I'm saying. At least you will have listened to it, you will have written a little bit about it, and might be able to come into class with some questions instead of just coming into class and being completely lost. Believe it or not, getting a little confused right now is not the worst thing in the entire world. So we're going to look at the definitions for these things first. Reversible reactions just simply mean a reaction that can happen going to the left and to the right. So it says up there where the reactants become products and products become reactants. You are used to seeing a reaction written like this one right here, where you have an arrow pointing to the right. You should know that the things over here on the left are the reactants, the things on the right would be the product. Well, if we turn that arrow around and we point it the other direction, it would turn the SO3 into my new reactant, and it would make the SO2 and the O2 become my new products. If you put both of those together, then you have what's called a reversible reaction. And reversible just means it can happen going to the right and going to the left. Or you could say forward or reverse. Forward refers going to the right like you're used to, and reverse would be, well, going backwards to how you're used to in the reverse direction. You can show reversible with two types of arrows. We have the double-headed arrow that's right here, or we have this one that I drew because I couldn't find a clip art for one, where you have like half of a right-hand arrow and half of a left-hand arrow, and you could put them together. So if you see either one of those, that means that this thing is making SO3 at the same time that it's making SO2 and O2. It's kind of cool. It's happening at equal rates. Equilibrium just simply means that you have things in balance. You have things that are equal. And so with the reaction, you have equilibrium when you have the forward and the reverse reactions happening equally. A couple of points. There's no change in the actual amounts. We're assuming like there's a lid on our system. It's closed. You're not actually adding new things to the reaction. The reaction doesn't stop. It keeps going. Forward and reverse reactions will balance each other as needed. If one of them gets out of hand, it'll compensate by doing the other one. The concentrations for the reactants and the products actually don't have to be equal for there to be equilibrium. It's not a balance in terms of like weight. No, don't think exactly like it would be like to balance out a boat. And if you add a catalyst, it would speed up the forward and the reverse reactions equally. How we get kind of complicated here is with LeChâtelier's principle, and I forgot to erase this from my practice session. So LeChâtelier's principle basically says that if you apply stress to a system, then the system will respond to overcome that. And I think of it in terms of like a seesaw. So if you have like a seesaw, or some people call it a teeter-totter, and you have like cinder blocks or something sitting on either side of it, if they're in equal amounts, then the seesaw will be balanced just like it is right here. But if you did something like, say, take this block off of it, like if we come in here and we erase this block, you should know that what this is going to do is this side is now going to sink down and this side's going to raise up because this one's heavier. And the only way for you to fix this would be to add some more weight back to this side to get us back to equilibrium. And we can kind of look at reactions that way. If we think of it as like the left side and the right side, if you do something to it, like change the pressure, change the concentration, or change the temperature, it's just kind of like unbalancing the seesaw. And what the reaction is going to have to do is get itself back in balance. Now, how we look at that is a little more complicated. The first one is concentration, and I've already written some things in here. It says any change in concentration will cause the system to adjust, and you should know that there's an understood 1 in front of each of these things in terms of coefficients. There's 1 mole of H2CO3 making 1 mole of CO2 and 1 mole of H2O. And if you think of it, in terms of these things, you're really just kind of looking at amounts. So I have some examples here, like if I add CO2, now the seesaw example works really easy here. If you think of this thing balanced to start with, and if I add CO2, I am adding something over here to the right-hand side. Well, in seesaw world, that's going to make the seesaw dip down on the right-hand side because it's now heavier. Well, if it was an actual seesaw, how you would make it come back to balance is, well, then you would need to add something over here to the left-hand side. So you have your answer. Your reaction would shift to the left. Because if I add something on the right-hand side and my reaction goes to the left, what that's going to do is turn the stuff on the right into reactants, and it's going to use them up and turn them into product. It's going to make more stuff over here on the left-hand side in order to compensate. If I take out CO2, well, the only way to fix that is to make more. And how do you make more CO2? Well, the reaction needs to head to the right in order to make more stuff that's on the right-hand side. If I give you a couple of more examples of this, if I have, if I take out H2CO3, the solution then is to make more of it. Well, to make more, I have to be heading to the left. If I take away H2O, the only way to fix that is to make more of it. So the way you make more is heading to the right. If I add more H2O, well, I need to get rid of it. So how I get rid of it is by heading to the left. We're going to practice a lot more of these in class, and I'll answer your questions to make sure that you get it. I think this example can kind of sometimes be one of the hardest ones. Another thing that we'll deal with is temperature. And in order for us to deal with temperature, it'll have to be written into the equation just like it is right here. So like the example from before, we couldn't do with temperature. You're going to have to know if heat is going in on the right or the left. And it says, basically, if you increase the temperature, it's going to shift to the side that will absorb heat. Because if you increase it, then it needs to decrease it. If we decrease the temperature, that's going to shift to the side that releases the heat. We should already know from previous conversations that we have had that if heat is written on the right, if it's going to the right, then heat is being produced, it's coming out. And if we're going to the left, well, then heat is going in. It's going in as a product. So if we add heat, if we raise the temperature of this reaction, then we've got to head to the left to take away heat. If it goes to the right, it's just going to make even more. That doesn't help me make things any better. If I decrease the temperature of the reaction, or I take away heat, then it's going to shift to the right, because going to the right makes more heat. This is kind of like a common sense type thing if you understand how to interpret the reaction. And then we have pressure. And I've already written on here too that if you change pressure, this only works for things that are gases. If you have gases, the amount of the gases is the only thing that matters. Because remember, we assume that all of the gas particles will take up 22.4 liters for every mole of gas, because basically they're so far apart that it doesn't matter what the size of the particles is. So if you decrease pressure, the general rules are written right here. If you decrease pressure, it's going to have to shift to the direction that has fewer molecules or fewer moles. I'm sorry, it'll go to the one that has more moles, more molecules or more moles. And if you increase the pressure, it's going to have to shift to the side that has less, because less molecules means less collisions and less pressure. More molecules will mean more collisions and more pressure. My numbers down here, well, there's 1 mole of N2 plus 3 moles of H2, making 2 moles of NH3. If I add up the 1 and the 3, that's 4 total moles of gas on the left and 2 total moles of gas on the right. What that means is that if I'm on this side, 2 moles is going to have less pressure than 4. 4 would make more pressure, 2 would make less. So there's really only 2 things that I can answer with this. There's not a whole lot of things that could be done. If you increase the pressure of the system, it's going to have to respond by heading to the right, because there's fewer moles on the right, and that would decrease pressure. If I decrease the pressure of the whole system, then it's going to head to the left, because when I go to the left, there's more moles, which means more pressure. There's really only 2 examples that I could do with this. I would have to come up with more problems to give you more examples, and we can practice that in class.